Hello, everyone. I'm Dcbuilder. I'm a research engineer at WorldCoin, where we're building a privacy-preserving proof-of-personhood protocol. And today, I'll be talking about zero-knowledge machine learning and its use cases. So zero-knowledge machine learning, it might sound like a buzzword, ZKML, two topics that we've been hearing on Twitter for the last year over and over and over. But is it an actual thing? Is it real? What does it do? What can you do with it today? So first, I'll sort of give a brief introduction about like the two topics, right? Like ZK and ML, and then how they combine together. So ZK, zero-knowledge cryptography, is a type of cryptography that allows us to prove computation, right? We can essentially have some program, and we can verify that this program executed correctly. In the context of blockchains, ZK has mostly been used for scalability purposes, right? We've seen rollups, ZK rollups more specifically, where you have some state transition function within some blockchain, right? So on the EVM, for example, we go from a block of height x to a block of height x plus 1, and there is a transition function that takes us there, right? So some transactions get executed, and we change the state on Ethereum, right? We can prove these transactions or these state transitions using zero-knowledge cryptography. And now, instead of having to re-execute all of these transactions on all of the computers of the network, like is the case for Ethereum, we can only just verify this proof very easily, right? It's very computationally inexpensive to verify this proof. And we can trust that this computation happened correctly. For machine learning, many of you have most likely seen ChatGPT, or some other models like image generation models, right, like DALL-E or whatnot. Machine learning is essentially a group of algorithms that are able to give some approximations to some problems by being trained on some data, right? So I have some function, and this function gets better at doing its job by me feeding it lots and lots of data, and it sort of learns some features about this data and allows me to perform some task. For example, like classifying whether an image is an image of a dog or a cat, predict some words after I give some input, right? In the case of ChatGPT, you give it some prompt, and then it gives you some output that tries to answer whatever you gave it in some prompt, and et cetera, right? With respect to machine learning, there's this concept of a heuristic. A heuristic is something that is a good enough approximation to some problem, right? Machine learning will never give you 100% accuracy, right? You have some training data, and using that training and the algorithm, you can essentially create some good enough approximation for the problem you're solving for, right? So if you have something like a classifier of images, there will be some non-negligible or really small amount of error rate, right? So if you have some predictor that some image is going to be a dog or a cat, then this algorithm will give you like a really good approximation, right? It will tell you, OK, I'm confident that this is 99% a cat or a dog, but sometimes it will make mistakes. So this is sort of like the concept of a heuristic. And now I'll sort of get into like what is ZKML. So ZKML, zero-knowledge machine learning. What it allows you to do is to create a proof, like a cryptographic proof, that this machine learning algorithm ran correctly, right? Or that it ran according to some specification that you have. Machine learning algorithms today, they're very black boxy. I do not know if they're actually running unless I download them to my own computer. I run them myself. So for example, if I am an API provider, right? I have some interface where a developer can just send a request for an output of some machine learning model, right? So I can upload to the internet an image of a dog or a cat, and this server will give me back a yes or a no, whether it's a dog or a cat, right? And I have no way of knowing if they're running some specific model that they claim they are. So instead, what you can do is just use something like ZK to provide a computational proof that they've used some model, for example, right? So why ZK? As I mentioned before, ZK gives us two main properties, really. One is verifiability of execution, so I can verify the correctness of some computation happening correctly. This stems from the cryptographic properties of completeness and soundness of snarks and starks. And the other part is being able to be zero knowledge, right? Like where the name comes from. Being able to hide parts of that computation to a verifier. In the context of ML, hiding computation would be, for example, hiding the weights of a model, right? I can train a neural network, and the neural network is just a function that has a bunch of weights, and these weights can be made private, but I can at the same time prove that I'm using some specific model and hide the weights. When we're talking about zero-knowledge machine learning, we're usually talking about proof of inference, right? In machine learning, there's two main actions you can do. One is training, right? Making this function better at doing its job. And the other one is inference, actually using that function to do some task, right? So in the context of ZKML, we're usually talking about proof of inference. The reason for this is because training is really computationally expensive, right? It takes millions of dollars, usually months of training on co-located data centers to just train some model. And zero-knowledge cryptography adds a lot of computational overhead, meaning that it's a lot harder to prove some computation than just performing that computation. However, on the other side, to verify, it's a lot cheaper. That's sort of the displacement that you're making. You're sort of pushing more computation on the prover and less on the verifier. So when we're talking about ZKML, we're just doing proof of inference because inference is less computationally expensive. You're just evaluating. You're not doing lots and lots of training processes. So I'll try to sort of just see like how people came up with ZKML, which is like what properties ZKML is constituted from and like how it compares with some other things. So we have three main properties in this diagram: computational integrity, privacy, and heuristic optimization. As I mentioned before, a heuristic is just some good enough approximation to some problem, right? In the case of ML, I can approximate, okay, the weather. I can predict the weather, so I can give some approximation of what it's going to be. But in reality, it may turn out to be something different. And to optimize this heuristic is to like improve this. This is what machine learning is all about, right? So if I combine privacy and computational integrity, I get what's ZK, right? In the case of ZK rollups, which may be not necessarily the best name because most ZK rollups today are not ZK, right? They're just validity rollups where they prove that some state transition happened correctly, but they're not hiding something or not hiding parts of that computation, like in privacy solutions, for example. If we combine computational integrity and heuristic optimization, or ML, we get validity ML. So this is just creating a snark or a stark, creating a proof that some machine learning model was executed correctly. However, we're not hiding any part of that computation or the weights. Everything is public. If we combine privacy and heuristic optimization, there's some subset of another field of cryptography called fully homomorphic encryption. What fully homomorphic encryption allows you to do is to encrypt some input, perform some computation on that encrypted input, and when decrypted, you can have the original input with the operation performed on top. So you can essentially perform computations on encrypted data without the person that's doing that computation knowing anything about that data. The difference between fully homomorphic encryption and ZK in terms of their properties is that fully homomorphic encryption will not give you verifiable computation. You'll not know that the computation was executed properly, or you cannot trust the person for doing that. And the difference from the ZK side of things is that the prover will always have access to the data that it's making proofs of. So it won't have privacy on the prover side. The prover will always have access to that private information. And if we combine all three, we get this sort of thing that's called ZKML nowadays. Right? So we can prove some computation that happened inside of some machine learning model, and we can hide parts of that computation. So this is just going over what I just said, if anybody wants to read it. So who is building in the space today? So I just borrowed a graph that was done by 7X Ventures. Essentially today, we're in a very early R&D phase, right? It's very early on. ZK technology has just become mature enough for us to start exploring, creating proofs of machine learning models. And the ZK space is moving at blazingly fast speeds and creating better proof systems, creating more faster and more performant provers, verifiers, right? We've seen this every day, right? How new proof systems come along, and like now, like ZK-Sync has improved their proof system, and all of these different projects are coming up with new solutions and making everything better. So machine learning is becoming more feasible by the day to create proofs of machine learning models inside of ZK, right? So there's several projects that are interested in ZKML. I'll mostly talk about the ones that are in the inference category, right? So Modulus Labs, Ezekiel, and Giza, for example. So these, what they're doing, they're trying to sort of go at machine learning from different approaches and trying to create zero-knowledge proofs out of them and creating better tooling and improving all of these. And now I'll sort of go, OK, like, this is all cool, nice technology, that's really interesting, but what are the potential use cases of this, right? Like, why is it useful for me to create a proof of machine learning model? So some of the use cases that are out there, it's early on, right? So currently, most of the actual use cases that are implemented today are mostly games or experiments, but some of the ones that are potentially able to make sense in the future are some of these that I list here. So machine learning as a service, transparency, right? So if I am a machine learning API provider, right, I cannot guarantee to the user that they're actually getting the API that I claim I'm providing them, right? So in the case of, let's say, OpenAI, OpenAI has a GPT-4 API, right? If I submit an input to that API and I expect some output, how do I know as a user that they're actually providing me the output of GPT-4 and not running GPT 3.5 on their servers and just essentially like cashing in the arbitrage of just running something that's cheaper to operate? Right? So instead of me having to trust that API provider, I can request the API provider to give me a zero-knowledge proof of that computation, and I can verify that succinctly. Another one is bringing machine learning on-chain. So as you all are most likely aware, blockchains are very computationally constrained. The computations you can do on them are very simple smart contracts, nothing too computationally expensive. And machine learning is really, really computationally expensive. And it's getting like harder and harder every year because people are pushing what's able to be done with machine learning. Therefore, they're requiring more and more compute by the day. So we cannot really do machine learning on-chain today, besides maybe some really, really basic like linear regression or logistic regression or some like really simple models. So what zero-knowledge machine learning can do is essentially create proofs of running these machine learning models off-chain. An analogy is like the same as rollups, right? Like doing this really expensive computation off-chain and then just bringing a proof of that computation on-chain. Therefore, we can bring the power of ML to the blockchain, right? We can just verify that proof on a smart contract, and cryptographically we can verify, okay, this machine learning model that's public did this computation. Another one that might be interesting is, for example, anomaly detection or fraud prevention. So there's like a plethora or a subgroup of small machine learning models that are dedicated to finding anomalies, right? We can train, in the case of something like chain analysis, you can train some models on some transactions, and you can sort of detect what is something that's never happened before, like an anomaly, or something that looks like fraud, right? There's machine learning algorithms that try to detect like fraudulent flows or some exploits or some weird transactions that never happened before. So what you can do with these machine learning models and ZK proofs is you can have a smart contract that has a sort of fraud prevention or anomaly detection verifier, like proof verifier inside of the smart contract. And if I submit a proof that some public model found an anomaly within some set of historic data, I can prove to the contract that, hey, I found an anomaly. You should adjust your risk parameters to like be more on the safe side. Or I can like pause the contract or any arbitrary logic that you may want to put into your smart contract. If we actually like, so all of these use cases were more like validity proofs, right? Like we're not hiding any part of the computation. We assume that everything is public. So now, what are some of the use cases where we can hide parts of the computation, like hide parts of the model, for example? So one of them is the centralized Kaggle. Kaggle is a platform where people can submit competitions for essentially getting the best machine learning algorithm to solve some task that the people that pose the competitions need solved, right? So I, as a Kaggle member, I can post a competition to find the best classifier of images of dogs and cats, and users that want to participate in that competition submit the best performing models they have, and the winner takes the bounty that the person that created the competition put up for it, right? So in the case of traditional Web 2, there is a centralized party, Kaggle, that essentially swaps these two, right? The person that creates the competition gives the price to Kaggle, and the person that submits the best price, or like the best solution, submits their solution to Kaggle, and then Kaggle gives the solution to the person that posted the competition and the price to the person that won the competition. So we can just decentralize this, get rid of the intermediary by just doing it with ZK proofs. The competitor can just post a proof that their model was the best performing one and atomically claim the price once the period of the competition has expired. Another one is this DeFi. So within decentralized finance, there's a lot of things where you might want to use machine learning. One of them is parameterization. So I don't know how well you're aware, but for example, there's protocols like Maker or Aave, and all of them have some hyperparameters that are tweaked on deployment or can be changed or set during its lifetime to sort of adjust risk parameters. Right? So instead of having or consulting with some really expensive products like Gauntlet, right? So if I go to Gauntlet, which is a sort of service provider that can adjust or like set these parameters using some math analysis at the beginning, then I can just have a machine learning model that can be sort of trained to optimize these parameters, these risk parameters within DeFi protocols. And I can just provide proofs that this model has outputted some new set of parameters at some new set of parameters. And I can just prove that, OK, these parameters were created by this machine learning model, and I can update the risk parameters accordingly. Another one might be yield routing, right? So things like year-end finance, right? So nowadays, you can only do very simple strategies using smart contracts. These strategies need to be public so that everyone that deposits money into these vaults, like yield vaults, that route liquidity across different protocols to maximize yield for the depositor, they are very basic. Like you cannot really create complex strategies because if you want to do complex computation, you run out of block space inside of the smart contract. So what you can do is you can set it to be a machine learning model, and whenever you want to update the sort of where we're allocating the funds within the vault, you can just run a machine learning model to predict where the best yield is going to be and just post a proof that some public model found the best yield to be in some other protocol. And using ZK, you can hide the weights of the model, right? So if you have some alpha, right, like if you have some model that is able to predict where the best yield is going to be, you can just hide the model and just use that one and just prove that this model that's hidden, that has the best yield routing, just update where the pool is going to be, right? And so I work at WorldCoin, where we're building a privacy-preserving proof-of-personhood protocol. And part of the challenges that we have is that we operate a hardware device that's called the orb. This orb sort of is an iris biometric scanner, and it has two main functionalities. One is to determine that a person is a real human being, and another one is that it's unique. And so we have a machine learning model that is able to sort of convert the entropy or the randomness that's encoded inside of a person's biometrics and create an embedding representation out of it, or a vector representation out of it. This vector, right, is created using some machine learning model. And if you ever update the model that creates these vectors or these embeddings, the output space of these vectors are completely different. So if a person gets registered once, they can use their world ID, right? They can use this privacy-preserving proof-of-personhood protocol. But if you ever update the model, you'd have to essentially go to this hardware device again and recompute this embedding or this vector that represents the uniqueness of your iris. And so this is suboptimal user experience. So another use case where ZKML might be useful is instead of me having to go to an orb again to recompute my iris code, if you ever update the model to be better, you can just essentially go to an orb once for the first time. You get onboarded, and the orb would essentially just save an image that's signed by its secure enclave inside of the phone, inside of the secure enclave of the phone, encrypted. And whenever there's an update to the model, you can just download the new model, download a prover for that model, and just create locally on your phone a proof that you computed this iris code correctly without essentially tampering with it. And since it has data integrity, because the original image that you use as input has a signature from the orb, so you cannot tamper with the original input. And then permissionlessly insert it into the smart contract by providing a proof alongside with the new iris code that you generated. Right? And so these are some of like the use cases that people are thinking of nowadays. And many more are emerging as time goes on. So where to learn more? So here I have three QR codes where like places where you can go to learn more. So one is the ZKML community, is a Telegram group that I created a few months ago, where people hang out and talk about ZKML. So people that have written research papers or are building the tooling and writing blog posts and whatnot, all of them get together and talk about ZKML there. Another one is Awesome ZKML. It's a GitHub repository with a README that has a list of all the different projects or code bases and tools and essentially like all the resources that have anything to do with ZKML. So if you want to learn more, I really recommend to go there. And I also, every single time I give this talk, I have a highlight article that I always want to bring up. So if anybody wants to learn more in depth about ZKML, that one leads you to an article written by 1KX about what ZKML is more in depth. Thank you very much, and I'm happy to take questions.
Hey, Dcbuilder, are you honestly telling us, for all the people in this conference who, first of all, have no idea what ZK is all about, that there's actually something new that fits in with the sort of AI world that also loads of people are talking about, and it kind of combines these two things together into this new thing that we're all going to have to learn about, which is called ZKML. Are you seriously kidding?
Yeah, it sounds like it's just a made-up buzzword. It's essentially like ZK proves any can prove any arbitrary computation, and machine learning is one such computation. So it's going to be hard to essentially make machine learning engineers aware of what ZK is, so that they can use ZK proofs. And then on the other hand, ZK engineers don't really know what machine learning is, so it's going to be hard to sort of teach about, okay, what does ZKML provide and who do you target for? But hopefully we can get past that pretty soon.
Hi, thank you for your talk. For the record, I have a PhD in formal methods, and I think that novel applications for zero-knowledge proofs to verify the correctness of computations like AI is actually a very nice thing. So thank you very much for your talk. I think, best of luck for the future of your research.
Thank you.